Okay, phosphorus 32 has a half-life of 14.3 days. If you start with a 5-gram sample, how much is left after 71.5 days? So what you have to do is you have to take the time elapsed, 71.5 days. I'm going to divide that by the known half-life, which is 14.3 days. When I divide this, I am able to determine that there are 5 half-lives. And so what I would do is I would take the original sample, 5 grams, and I would divide it in half 5 times. So in doing so, let's see. So if I start with 5 grams, after the first half-life, there would be 2.5. Okay, divided by half would be 1.25. Divided by half would be 0.625. Divided by half, oops, that's a half, that's not a 5. Divided by half is 0.3125. And divided in half one more time. And your answer should have 3 significant digits because you have 14.3 is 3, 71.5 is 3, 5.00 is 3, so I'm going to round my answer to 3 sig figs. 0.156 grams. Make certain you use unit labels. Okay, here's another half-life problem. It looks like the time elapsed is 40 days. I'm going to divide this by the known half-life, which is 8 days. So this tells me, once again, 5 half-lives have passed. And so I want to know how many milligrams are left of a 160 milligram sample. So I'm going to take 160 milligrams. I'm going to divide it in half 5 times again. So after the first half-life there would be 80. After the second there would be 40. After the third there would be 20. After the fourth there would be 10. And after the fifth half-life there are 5 milligrams remaining. And this is the correct number of sig figs because if you look, 8.0 has 2, 160 written that way has 2, but the number 40 only has 1 significant digit. Only the 4 is significant, the 0 is not. It does not have a decimal after the 0, so you must round your answer to 1 sig fig, 5 milligrams. Okay, in this problem, we know the half-life and we know the original mass of a sample, how much was left at the end. If you take the original sample, so 0.48 milligrams, I want to see how many times I need to divide it in half to get 0.06 milligrams. Okay, so if I divide this in half the first time, I get 0.24. The second time is 0.12. After the third half-life, 0.06. And so I know that 3 half-lives have elapsed. Okay? Well, according to the formula, I know the known half-life is 5,715 years. I do not know the amount of time that has elapsed, but I do know that this is 3 half-lives. And so what I'm going to do is rearrange this problem to solve for x. So what I would do is I would take both sides times 5,715 years. Okay, that's going to cancel. 5,715 years. If I multiply that by 3, my calculator is going to spit out 17,145 years. Let's see, according to sig figs, 5,715 has 4.48 milligrams and 0.060 milligrams. Both have 2. Therefore, I must round my answer to 2 sig figs. 17,000 years. Okay, the symbol, mass, and charge for alpha, beta, and gamma. Okay, you will notice that alpha sometimes is symbolized with the Greek letter alpha. Sometimes it's represented with just an He, because really an alpha particle is a helium nuclei. Beta, you will see it as the Greek letter beta. Sometimes, because really they are just high-speed electrons, you will see the E with a 0 and -1 subscript, because they really are an electron. Gamma is this Greek letter gamma. As far as mass, alpha has a mass of 4. A beta particle has the mass of an electron, which is 1/2000th. Gamma is not matter. It's a ray. It's it's electromagnetic radiation, so it has no mass. It's simply energy. Because an alpha particle is a helium nuclei, that means it has no electrons. Therefore, it has a charge of +2. A beta particle, being an electron, has a charge of -1. Gamma, no charge. Speed, alpha particles are fairly large and they're fairly slow. Beta particles move relatively faster, and gamma, being electromagnetic radiation, travels at the speed of light. The ability for these types of particles to cause ionization. Alpha are very high, beta has medium, gamma has no ionization power. Penetrating power, the ability for it to pass through objects. Alpha, very low. Notice you can stop it with a sheet of paper. Beta is medium penetrating power. You can stop it with like a sheet of aluminum. Gamma has very high penetrating power. You need several inches of lead to stop gamma rays. Okay, to balance this nuclear reaction, you will notice thorium-234 undergoing beta decay because it's emitting a beta particle. So let's see, it is, what number plus 0 is 234? Well, it's 234 is the mass. And then what number plus -1 is 90? Answer, 91. So that makes this protactinium. In this example, we have polonium-218 undergoing alpha emission. You'll notice that's an alpha particle. So what number plus 4 is 218? And that is 214. What number plus 2 is 84? That's going to be 82, which makes this lead. Alright, number 34, it looks like we have lead-210 decaying, and it looks like the product is going to be mercury-206. And so what number plus 206 is 210? 4 is the mass, and what number plus 80 is 82, which is 2, making this alpha decay, a helium nuclei. Alright, in this problem it looks like we have thorium and an alpha particle being the products of a decay, so we want to know what the original substance was. 4 plus 234 is 238. And then 2 plus 90, 92. This is uranium. Alright, in this example we have praseodymium undergoing some kind of radioactive decay. Okay, so I have 140 and 140, so 0 is going to be the mass of this particle. What number plus 58 is 59? Positive 1. We didn't really talk about this type, but what this is called, this is a positron. Basically what a positron is, it is a positively charged electron. It's a proton without any mass. So, positron emission. Sometimes referred to as electron capture. Okay, the difference between nuclear fission and nuclear fusion. Fission, you have a large particle that is split into 2 smaller atoms. Generally, a fission reaction, you will see that something that initiates the reaction, like this neutron striking this nucleus, is also the product to kind of continue a chain reaction. Fusion is really the exact opposite. Basically, a fusion reaction occurs when you have two smaller nuclei fusing together into a larger, heavier nucleus. So fission is the splitting, fusion is the joining. So large nuclei, small nuclei, splitting apart, putting together. And this would be nuclear fusion, generates heavy elements from lighter. The temperature that is required for fusion to occur, so it takes tremendous amounts of heat, tremendous amounts of energy for these hydrogen atoms to fuse together to become helium. It is generally accepted that it takes 100 million degrees Kelvin. Kelvin is a temperature unit used in chemistry. One of the reasons why Kelvin has no negative values. You'll learn why that's important later when we get into the gas law unit. The only thing that determines really the life cycle of the star is its mass.